Okay, Chapter 3, Section 1, the constant E and continuous compound interest. Okay, so this section is going to rely on some content that hopefully is familiar to you guys by now. So we have to understand E, and we also have to understand compound interest. So hopefully you're already uh, kind of familiar with those ideas. So let's take a look at E. So E. E is described as this number, 2.71728 dot 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 dot. Most commonly it's just kind of rounded. Most often it's just kind of rounded to be E equals to 2.718 as a rounding of this. But we know that this is an irrational number. It goes on forever and ever and ever, never stops. And there's never any repeating patterns. It doesn't start to repeat itself, right? It's an irrational number. And there are different ways in which we can arrive at this number. This is one of the most common ways to define what E is. You might have seen it before. You might have run into it, based on a different definition. But now that we know all about limits, we can appreciate this definition a little bit more. So E is the limit as n goes to infinity of this function, 1 plus 1 over n to the power of n. Okay, so let's explore this a little bit and see how this leads to this number. Okay, I'm going to use Excel. Okay, so in a simple Excel sheet, what I've done is I've identified this column as n. So this would be n equals to 1, n equals to 2, n equals to 3, and so on and so forth. And then in this column, I've put in my equation, 1 plus 1 over n to the power of n. So for instance, when n equals to 1, we're going to replace the n with a 1. We'll end up with 1 plus 1 over 1, which is just going to be 1. 1 plus 1 is 2 to the power of 1. So the answer is just going to be 1. It's going to be 2 for that case. When n equals to 2, we'll have 1 plus 1 over 2, which is 1 plus 1 half. 1 plus 1 half is 3 over 2. The power of 2, which will give us a 9 over 4, which then divides to 2.25. Okay, so we want to expand this, continue. So when n equals to 3, when n equals to 4, right? Okay, so let's expand it this way. When n equals to 3, we'll get this decimal, 2.37033737. And when n equals to 4, we'll get this decimal, 2.4444. Okay, but we're interested in seeing what happens as n goes to infinity, as this number gets really, really, really large. So I'm just going to expand this out, really go crazy. Okay, so I'm just going to go through and notice that as I scroll down, the values of n are getting larger and larger in the 60s, in the 70s, in the 80s. Okay, so n is increasing. And look at the resulting outputs of that equation. They always start with a 2. That never changes. And then the first decimal afterwards is a 7, so 2.7. The one after the 7 is stable at this point at 1. The one after that is changing a little bit. So it's always growing. One pattern we notice is it's always growing. But as we let n get bigger and bigger and bigger, the decimals begin to kind of settle into place. So this is after n equals to, in the 500s, almost 600 at this point. And the 2.71 is stable, but the one after that is still growing. So let's really grow. Let's go back to the top here. Instead of counting by ones for n, 1, 2, 3, let's make it by 100s. So it'll go from 1 to 101, and then I want to make that grow to 201, then 301, so it'll really grow fast. So let's go to town here, go way, way down. So again, as I scroll through, this time the inputs are growing much faster, 101, 201, 301. And as I look at the resulting outputs, it's always going to start with a 2. and then decimal, and then a 7, then the 1, then the 8, then the number after that, you know, starts to get a little bit more, becomes a little closer to the number we're interested in, the output we're interested in. Okay, so we can see that as this number, as the input values begin to grow to larger and larger values, this resulting output is approaching something. Okay, maybe let's try it in a different way. Okay, so we never get to the answer. The input could always be bigger, and the output would always change, except that the change is decreasing. It's getting closer and closer to a number. Let's do it in a different way. Okay, so on Desmos, I'm using the table function here. So I'm using my variable n, and here is the formula that we need to work with. So when we type in a 1 into here, it'll replace the n with a 1. So we'll end up with 1 plus 1 over 1 to the power of 1. And then that'll result in 1 plus 1, which is 2 to the power of 1. So just 2 is our answer. Okay, so that's the first result. When n equals to 2, we'll get 1 plus 1 over 2 to the power of 2. So 1 plus 1/2 is 3 over 2 to the power of 2 will be 9 over 4. And when we divide that into a decimal, we get this one. Okay, and then for 3, well, we plug a 3 there. We calculated this is the decimal we're going to get. And then for 4, and then for 5, and then for 6. Okay, so one thing we want to notice is that the number is always growing, right? So it starts off at 2, then 2.25, then 2.37. It's always growing, but the growth is slowing down. Notice that was from 1 to 2, we grew by 0.25. And then from 2 to 3, we only grew by about 0.12. And then from here to here, we only grew by about 0.07. So the growth, the change is slowing down. That's one thing to notice, but it's always increasing. Increasing, but the growth is slowing down. And also we're interested in the limit as this n value grows to infinity. So we want to see what happens as we input larger and larger and larger and larger numbers. So here's just the first 10 of them. So here it's growing. So what happens when we get even larger and larger and larger? We can graph these points. So here are these first 10 points. And I'm going to change the scale here so we can see it better. So let's change. Okay, so I changed the scaling a little bit so it's a little easier to see. Here is the point 1 comma 2 and the point 2 comma 2.25 and so on and so forth. So now we can get a better visual of the fact that they are increasing. They're always on their way up. They're increasing as n goes toward infinity. As n gets larger and larger, the outputs keep getting larger and larger and larger. But their growth is slowing down. Look how much growth there was from 1 to 2. There's a big gap. But then from 2 to 3, it's a smaller gap. And from 3 to 4, there's a smaller gap, right? A gap in the y-axis direction. So their growth is slowing down. We could see that. But again, we're interested in seeing what happens as this grows toward infinity. So let's grow by even larger amounts now. So let's jump by 10. Okay, so just changing the scale, we see we started here at 1 comma 2, and then very quickly it has been growing, and then way over here at 100 we get 2.7048. Okay, so if we keep going, we see that there's a pattern here that begins to emerge. So let's graph this guy. So this would be y equals, okay, well, doesn't like n, so let's change this to x. Okay, so now if I graph this line, right, I just changed the n to an x because Desmos prefers that. We see that here are are the values. And we see that there is a horizontal axis somewhere around there, and that horizontal axis is where these values are growing toward. That value there is the value that we're interested in. Okay, so y equals to e is that horizontal axis, where e equals to this number, right? So we wanted to know where are these points growing to as I input larger and larger numbers. Now let's come back over here and grow by even bigger numbers. So how about if this is 100, this is 200. Okay, we see that now if I'm going by multiples of 100, the outputs are getting really, really, really close to this number, 2.718, right? As the input values grow larger and larger and larger, the output values are getting infinitely close to this value here. So here's a nice little graphic I found on the internet that does a nice job of presenting E. So we have the formula for it, right? We have 1 plus 1 over n to the power of n, and we're interested in seeing what happens as n grows toward infinity. So we have a nice table here with 1, 2, 5, and they jump to 10, 100, 1,000, 10,000, 100,000, and we see the resulting outputs are getting larger and larger and larger and closer to the number we know to be E. And then we have a nice little graph for it as well. So we see that the numbers are growing, and they're always going to be approaching this green bar, this horizontal asymptote, and that value is the value of E. Okay, so hopefully that gives you a pretty good sense of what E is. There is no end. This gets infinitely close to the green line, but is never going to actually be equal to the green line. So the farther out you go to the right, the closer these two get, the smaller the gap gets, the closer this function will get to the value we're interested in. So you can get infinitely close, but you can never actually be equal to it, so there's no end. And there's a lot of value to the number E. So we'll see lots of ways in which we can apply it. Okay, so let's move on. Okay, so hopefully now we remember E and we're comfortable and happy with E. If you are asked to round and approximate, then we use 2.718. If you want a more precise answer, there's a button on our calculator that has this lowercase e. In math, we use the letter E to represent this number and nothing else in math. That's how important this is. We gave it its own special letter, and then we retired that letter. That letter cannot be used for anything else but this number in math. So it's a really important number. Probably equal to, maybe just as important as pi. Pi is another very important irrational number that appears all over the place in math. So it's got its own unique symbol. Okay, so just keep that in mind. Okay, so one of the applications for E is compound interest. So hopefully this looks really familiar for you as well. So hopefully you've worked with these two formulas before. There's a formula for simple interest and there's a formula for compound interest. So these are the common variables used with these two formulas. So capital P represents the principal, the initial amount invested. R represents the annual percent interest rate. Notice that this is annual. It's always annual, per year. That's just a, it's common in the business world to provide all interest rates in terms of a year, just for consistency. That way, when everyone is clear and there's less opportunity to make mistakes. Same with time. Time is always given in years, and it matches that. So the interest rate and time is always by default given in years. And then we use the letter M to represent the number of compounding periods per year. And then capital A is used to represent the amount realized at the end of the time period. So the complete balance on your account at the end of the time period. Okay, so simple interest would follow this formula. It's A equals to P times 1 plus RT. Um, so we'll see an example like this in a second. And then compound interest follows this formula. A equals to P times 1 plus R over M to the power of MT. Okay, so let's look at some examples. Suppose $1,000 is invested into a savings account that pays 5% interest per annum per year. Calculate the amount of the account after 20 years. Okay, first of all, simple interest. Simple interest is simple. So we're going to start off by, let me zoom in here. Simple interest, the formula is A equals to P times 1 plus RT, like that. The R, in this case, R is presented to us as 5%. Remember that we have to convert that into its decimal representation of 0.05. T is in terms of years, and they say 20 years. Now, some tricky word problems might say a year and a half or 36 months. So you're going to have to convert that into years to use it into the simple simple interest formula. So be careful with that they match. But they do in this they do in this case, T equals to 20 years. And P is the amount of the original principal. So this formula then is going to be that A equals to 1,000 times 1 plus 0.05 times 20. This is where the R is right here, and the T is right there. Maybe I should put parentheses around it. The T is right there, 20 years, interest rate of 5%, and the P is right there. Okay, so now we can just punch it into our calculator and get our answer. So we'll get 0.05 times 20 plus 1 times 1,000. We get 2,000. A equals to 2,000. Okay, so just kind of following my formula, that's how we get that. But since it's simple interest, there's another simple way to do it. Simple interest means that we just get 5% of the 1,000 every year for 20 years. And note, so this is following the formula, I put or, we could say 5% of 1,000, that's going to be 0.05 multiplied by 1,000, which equals to $50. So we're saying we're going to get $50 each year, every year for 20 years. So $50 each year for 20 years. Well, that's 20 times 50, which equals to 1,000. So you're going to earn $1,000 in interest, plus your original $1,000 that you invested gets you to your final deposit, the account balance after 20 years. Okay, so that's simple interest. You're going to make the same amount every year, 5% of the 1,000, and you make that every single year for 20 years. You're going to get $2,000 at the total in your account, $1,000 in interest, $1,000 from the original amount invested. Together, they give you an account balance of $2,000 at the end of 20 years. Okay, now compounding is a little bit different. Compounding means that there's going to be a period of time, a period in which at the end of that period, they're going to deposit your interest earned into your account, and then the following period, you're going to get paid interest on both the original amount invested as well as the new amount of money deposited into your account from the previous interest earned, right? So in other words, over here in the simple interest, each year you were getting $50, every year $50. So at the end of 1 year, your account had $1,050. At the end of 2 years, you would have $1,100. Whereas with compound interest, things start improving at the second year. Right, so let me put over here. So with simple interest, let's put T over here, and then the balance. So at the end of year one, you're going to have $1,050. You made $50 in interest, right? Simple interest. At the end of 2 years, you'll have $1,100 because you add an extra $50. At the end of 3 years, you'll have $1,150. Okay, you always get $50 every year. With compound interest, we're going to say, well, in the first year, you only earned $50 because you had $1,000 invested. But coming forward over here, now we want to earn interest on this as well. So you're going to earn a little bit more interest. You're going to earn an extra 5% on the $50, which is an extra 50 cents. So with compound interest, this one is simple. With compound, at the end of 1 year, you'll still have the same amount, $1,050 still, because you earned $50 from that first year, and you're only compounding annually. But at the end of the second year, you're going to earn a little bit more because you're going to also earn interest on the interest earned the first year. That's what the compound is referring to. And so 5% on $50 is equal to $2.50. So at the end of the second year, you'll have 1,102.50. Right? So with simple interest, you would have only had $1,100. But with compound interest, you're going to earn an extra $2.50, which comes directly from the interest earned the first year. And so you grow just a little bit more. Doesn't seem like much, but it will add up. Okay, so the following year, the third year, you're going to earn interest not just on the original 1,000, like you would in the simple interest case, but now you're going to earn a little bit more interest because you're going to earn interest on this extra $102.50 that's sitting in your account. So an extra 5% on this would be a little bit more than $5. So the extra interest earned, the extra 5% on just the extra $102 is equal to $5, and about 13 cents. From here to here, the extra amount was $2.50. That's just the interest on that $50. Whereas here, the extra interest on the $102 is going to be this $5.13. So at the end of 3 years, your account balance is now going to be equal to $1,155.13. You see how you're slowly growing faster, right? If you just had simple interest at the end of 3 years, you would have 1,150. 3 times they paid you $50. Whereas here, in this case, you're growing a little bit faster because the amount of money they're depositing in your account is also earning interest, right? The interest paid is gonna earn interest. Your money makes money for you. That's the key to rich people. They just have a bunch of money sitting in their account, and all they have to do is let their money make more money for them. It multiplies by itself, right? And it doesn't seem much when we have $1,000, but if this was, $1,000 million, 1 billion, well then that would be a lot of money just growing. Okay. All right, so back to this problem. We don't want to have to calculate it out like this every time, so we have a nice, simple little formula for this. So let's just follow our formula. So the formula for compound interest is A equals to P times 1 plus R over M, power of MT. And compounded annually means that M equals to 1. So here, M equals to 1. So we just replace that with a 1 and that with a 1. So we'll get A equals to P times 1 plus R to the power of 1 over 1, and then 1 times T. And so we have everything we need for our little case. So for us, we have A equals to 1,000. That's the initial amount invested, times 1 plus R, which was the 0.05 over 1, raised to the power of 1 times 20 years. Okay, so now we could just simplify this a little bit. This is A equals to 1,000. 1 plus 0.05 is just going to be 1.05 to the power of, and then 1 times 20 is just 20. So we just have to figure out what this is. So A equals to this amount. So let's get our calculator. Clear. So it'll be 1.05 to the power of 20. We get that times 1,000, 1, 2, 3, and we get that. 2653 points. Let's just round it to 30 cents. So this is going to be $2,653 and about 30 cents. Okay, so we can really see the difference between an account that compounds annually. So at the end of each year, there's like a statement on your account, and they go, okay, at the end of this year, let's deposit some money into your account, what you've earned this year. And then at the end of second year, they do the same thing. But now you have more money in your account because they paid you interest the first year. So now the interest is also, the amount of money that you earned in interest the first year is going to make you even more money. And that growth results ultimately in having a much bigger account at the end of 20 years. Okay? So at the end of 20 years with simple interest 5%, you'd have 2,000 in your account. At the end of 20 years with 5% interest compounded annually, you'd have $2,653.30. What about compounded daily? What if every single day, at the end of every single day, what about compounded daily? What about a case where at the end of every single day, your bank takes stock of your, like a statement that you get, like a daily statement of your account. They pay you into your account the interest you've earned for that day. So by day 2, your account is already a little bit bigger than what you started because they've already paid you your interest from day 1. Therefore, you earn interest on the interest earned on day 1. And then on day 3, your account balance is already a little bit bigger because you've been paid twice already. And so now the amount of money you earn is going to grow faster. Okay, we could do a table kind of like this and work it all out, but I'm not going to do that. Hopefully all of this is review anyway. So let's just jump right into our formula and see how our formula gives us our answer. So we have that the compound formula is this: A equals to P1 plus R over M to the power of RT. And for us, M is daily. Daily means 365 days, right? There's 365 days in 1 year, so that's what we're going to do here. And we already have the value of R, and we already have the value of T. So this would mean that A equals to A equals to 1,000 times 1 plus 0.05 all over 365 to the power of, oops, this is not an R, this is an M. To the power of 365 times 20 years. Okay, so now let's simplify this and interpret what that means. 1,000 plus blank, I'll leave that blank for now, to the power of blank. Okay, I need to figure out what this is. 0.05 divided by 365. 0.05 divided by 365 gives us this decimal. And notice that it's e to the power of -4. So that means we move this decimal over 3 spaces, or we can leave it in scientific notation. So this would be 1369863. I'm just going to stop at the 6.3, so I'm going to rewrite it this way. This is equal to 0.123, and then 136, let's erase this guy, 1369863, 9863. Okay, and then I'm going to multiply these two things, 20 times 365, 20 times 365, and I get 7,300, 7,300, 7,300. Okay, now let's notice what we've done here. Up here, when m was equal to 1, where we were just compounding annually, we got to this point, and we had 1 plus 0.05 to the power of 20. And so the 0.05 was the interest rate per year times 20 years. These two match. This was in years, this was in years. So how many times would they create a statement and deposit money into your account? Well, it would be once a year for 20 years. There would be 20 statements to deal with, right? Because it's compounded annually. You would have 20 statements, one for each year. That's the period of time when they deposit money into your account. Okay, now if we want to turn it into a daily situation, then what we do is we take the annual interest rate given divided by 365. This gives us the daily interest rate, right? When I divided these, this gives me the daily interest rate. And so if each day they give you a statement, they figure out how much interest you've earned, they deposit it into your account, and so your account balance increases every single day. At the end of 20 years, you would have 7,300 statements, like bank statements, right? We call these periods. And they match, right? This is every day. There are 7,300 days in 20 years, and we're figuring out the daily interest rate. So these two things have to match. That's what we're going for. Okay, now in order to get a nice precise answer, it would be better not to convert this into a decimal, just to leave it in your calculator the way it is, and just kind of calculate the whole thing out. I just wanted to spell it all out, just to point out that these two things must match in terms of their period. If they say monthly, then we're going to figure out the monthly interest rate by dividing the annual by 12. That'll give you the monthly interest rate. And then we multiply the number of months times the number of years, so in this case 20, and we'll figure out how many statements there will be, how many periods there will be, where those period lengths match the interest rate given. Okay, so daily, monthly, quarterly, annually, biannually, and so on and so forth. Okay, so let's go back to our calculator and find an answer for this guy then. So this is going to be 0.05 divided by 365. That gives me my daily interest rate. And then according to the formula, then I add 1 to that. So that'll give me the sum of this whole thing. And then I want that whole thing raised to the power of 7,300. Raised, so the previous answer, raised to the power of 7,300 gives me that number. And then that number gets multiplied by 1,000 times 1,000. And that's the number I land on, 27.18. And then just to round, we'll say 10 cents. 27.18 with 10 cents. Okay, so if you're compounding your money every single day, at the end of 20 years, you will have a total of 7,300 statements, 7,300 times that the bank deposited your interest earned into your account. Therefore, it's growing a little bit faster. Your previous money earned is also going to be making money at a more efficient rate than it was when you were just doing it annually. And so it's going to grow faster. At the end of 20 years, this would be the balance on your account. Okay, so we could see that simple rate is the worst. At the end of 20 years, you only have $2,000. When we compound, okay, compounding once a year, very popular in business, compound once a year, okay, much better, much better results. And then compounding daily is a little bit better. Again, when you're only talking about $1,000, it doesn't seem to make that big of a difference. But if we're talking about big money, millions and millions, hundreds of millions, billions and billions, then that tiny little difference can translate into tens of millions of dollars, hundreds of millions of dollars. So it can be really important. So here is the same results in, kind of nice and typed out. Okay, let's do another example. Okay, a sum of $1,000 invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. All right, let's just work out one of them, and then we'll see a table that has all the others. Again, I hope this is review, so I hope this is going smoothly for you. And really, we just want to see a pattern of what happens as we compound more and more frequently. Okay, so let's just focus on the, let's say monthly. We did daily a little bit ago, so let's focus on what it would look like if we do it monthly. So the formula is A equals to P1 plus R over M to the power of MT. And for us, the P is still equal to 1,000. And R is now equal to 12%. Remember, we never put a 12 in there. We have to convert it into its decimal representation, which in this case is 0.12. And then M is monthly for this case, monthly, which means that it happens 12 times in 1 year, 12 times per year. Okay, so M is just going to be equal to 12. Then T is 3 years, 3. Okay, so remember that the rate and the time is always presented in our word problems. Well, almost in the formula, it's always represented as years in terms of years. So the annual rate and T in terms of years. Now the word problem could be a little trickier. They could have said, find the amounts in the account after 36 months. So certain things like to go by months, like mortgages. If you ever look at mortgage documents, they often refer to the number of payments. There's 360 payments, there's 590 payments, whatever. They turn their years into the number of months required for the mortgage. Okay, so now all we have to do is plug it into here. So we get that A equals to the initial $1,000 invested times 1 plus 0.12 divided by 12 to the power of 12 times 3. Okay, so let's convert that. We get A equals to 1,000 times 1 plus, now 12% divided by 12, that's going to be 0.01. That's 1%. So 12% annually means 1% per month. Nice and convenient. And then 36 times 3 is, 12 times 3 is equal to 36. Okay, so again, remember what we've done here is we've made these two match. We've turned it into the daily interest rate. So now this is, the monthly interest rate. And now this guy up here is the number of months in 3 years. Number of months in 3 years. I think of it as the number of statements because I think of it like a bank account. So if they're compounding my interest every single month, I should be getting a statement every single month. I should be told then my account balance has increased every single month because they're paying me my interest at the end of each month. And so at the end of each month, my interest earned is going to go up a little bit more than the prior month because every single month there's a little bit more money in my account. Okay, so make them match. That's what the formula does for us. We get the monthly interest rate, the number of months. So in 3 years, if I'm compounding monthly, I should expect to have 36 periods, 36 statements, right? Or 36 periods. And these have to match here. These are the monthly interest rates. This is how long a period is. A period is 1 month. In 3 years, there are 36 periods. Okay, so now that we have that, we punch it into our calculator and get a more precise answer. So it's going to be 0.01 plus 1. That'll be this part here, raised to the power of 36. And then we multiply that by 1,000. 1, 2, 3. 1,000. Okay, so get 1430.77. Okay, so $1,000 invested at 12% interest rate per year for a period of 3 years, compounded monthly, will mean that at the end of the 3 years, we will have a balance of $1,430.77. In other words, $430.77 is the total amount of interest earned in that 3-year period, right? That's really close to, well, it's a little bit more, a tiny little bit more than 43%. There's a 43% increase in that 3-year period. Okay, well, we could do the same thing for annually, semi-annually, quarterly, daily, but I think you get the point, and hopefully all of this is review. So let's just look at a nice table that has all of these different ones. Okay, so here's a nice table that has the results for a variety of compounding options. So remember, it's $1,000 invested for a period of 3 times. That stays the same. And the interest rate is 12% per year. That stays the same. The only thing that's changing is how often we compound our, how often our investment is compounded. So annually means once a year. At the end of 3 years, that means there's only 3 periods, 3 statements to deal with. And this is going to be our balance at the end of 3 years. Okay, so this just is replacing the M with a 1 in our formula. Right, here's our formula, our general formula, replacing the M with a 1. So replacing this M right there with a 1 gets you to this formula right there, and that's going to be our balance. Now semi-annually, so twice a year, every 6 months, that means we go back up here, replace that M with a 2. So if we replace the M with a 2, 12 divided by 2 is going to be 6%. So 6% every 6 months, the 6-month interest rate is 6%. In a 3-year period, there's going to in 3 years there would be 6 periods to deal with, right? So if your bank account gave you your interest every 6 months, in 3 years you would expect 6 statements, 6 periods, and the interest rate would be 6% in that frame. Okay, quarterly means every 4 times a year, every 3 months. So if we divide this by 4, we'll get 3%. So your interest rate, your quarterly interest rate is 3%. And in a 3-year period, we would expect 12 different quarters. And this would be your balance. Again, that's just replacing the M. That's just replacing the M with a 4. Then monthly, that's replacing the M with a 12. That's the one we did over here. Replacing the M with a 12, we get to this balance. And finally, if we replace the M with a 365, we would get this equation. And so that would be our balance. Okay, one of the things to notice is that the more frequently we compound, as N gets larger and larger and larger, the balance is growing, right? It's getting higher and higher and higher. So the more often we compound, the more beneficial to the owner of the account, right? Assuming that this is positive cash, this could also be word problem twist it around and say that this is a debt that needs to be paid. So, for example, like a credit cards are most often compounded monthly, but maybe there's some great credit card out there that's only compounded once a year. That would be awesome. On the other hand, there could be a credit card that's compounded daily. That would not be so awesome. Okay, so it could be flipped around and say that this is a debt, and then that wouldn't be so good. But if it's a positive cash, if it's an investment, then it benefits you to compound it more and more frequently. Okay, so this pattern is what we want to focus on. What if we let the number of times we compound grow, right? Get infinitely large. What happens at infinity? Continuously compounded every single fraction of every second of every minute, always compounded. Where does this formula go? Okay, that's what we're going to do next. Okay, so far we reviewed the definition for E. So remember that if we have E is defined to be the limit as n goes to infinity of 1 plus 1 over n, the power of n. And we know that that limit is going to be equal to approximately 2.718, But normally we stop there, but this is E. Now, I would like to note that this is just a dummy variable, n. There's nothing special about n, right? N. So exactly the exact same number can be represented using a different letter, right? Or E equals to the limit as, how about Q? Q goes to infinity of 1 plus 1 over Q to the power of Q. Well, that's still going to be 7.18, right? Nothing special about the letter Q. Or we can go to a different letter. We can go to W. Limit as W goes to infinity of 1 plus 1 over W raised to the power of W. Same thing. It's still going to be equal to the number E. Okay, so that's one thing I wanted to point out. Nothing special about the letter N. It's about the concept, the idea expressed rather than the specific letters. And of course, we know algebra loves X, so we might see it in terms of X. As X goes to infinity of 1 plus 1 over X to the power of X, same thing. They're all E. Okay, the next thing we learned is that we have a formula for compound interest. We know that A, the balance of our account, is equal to P times 1 plus R over M to the power of MT. And we saw that if we let R equal to a constant, we fix that, and we let T equal to some constant, right? We fix it, leaving that alone, and we let P equal to some constant. So the only thing we focus on is M, right? The principal amount invested stays the same. R is some constant that's fixed. T is some constant that's fixed. We only focus on how our balance will change based on M. We notice that as M gets bigger and bigger and bigger, the account balance got bigger and bigger and bigger. Okay, so we want to think about what happens as the number of times we compound increases to infinity. So that's what we're interested in. Let's find the limit as M goes to infinity of this formula. P times 1 plus R over M, power of MT. Okay? And this is still going to be A, the account balance that we get when the compounding goes to infinity. Okay, that's what this is saying. Okay, so this formula here represents the account balance of a P investment, so P dollars invested at a rate R for T time as the number of times compounded goes to infinity. That's what we want to work with. Okay, so we want to do a little bit of algebra magic here and figure out what is happening to this. So the first thing I want to think about is that the M is, this is a multiplication of, So the first thing I want to think about is that all of this is being applied by this limit. However, this p has nothing to do with m. So we can pull it out in front, right? Our understanding of limits tells us that we're allowed to do that. So this is going to be equal to p times this limit, the limit as m goes to infinity of 1 plus r over m to the power of mt. Okay, next what I want to do is introduce a little number right here, which I'm going to call r over r. I'm allowed to do that. R over r. That's another version of 1, and I'm multiplying the exponent, and I'm going to distribute it a little bit. So I'm going to rewrite it this way. This is going to be equal to a equals to p times the limit as m goes to infinity of 1 plus r over m to the power of, and I'm going to tuck in that m over the r, times an rt. Right? Just kind of distributing this a little bit. Allowed to do that. Okay, and so now I'm going to replace this with the letter n. So let's think about n. Let n equal to m over r. So if you think about letting m divided by r equal to n, then if we flip it around, we also know that 1 over n must be equal to r over m, right? We can do a little bit of algebra there to figure out that these two must be true. So I'm going to come back over here and replace these two. So here, m divided by r, this is going to be replaced by this n. N equals to m over r. Whereas this one is the other way around, r divided by m. This one is going to be replaced by 1 over n. Okay, let's copy that again. So now a is going to be equal to p times, and I'm going to leave this alone for a second, and I'll say that this is 1 plus 1 over n to the power of n. Oh, let's put it in green. This is going to be 1 over n raised to the power of n, and then that whole thing gets multiplied by rt multiplied by m. Because there's no more m's, I got rid of them. So it wouldn't make sense for me to say the limit as m goes to infinity because there's no more m's. What are you talking about? Okay, but we did do a substitution here. So notice that if r is a constant, r is some interest rate that's given to you that doesn't change anymore, like it's 12% or 4%, it's no longer a variable that will move, it's some constant that will be provided for you. So now if we think about what happens as m goes to infinity, as m gets infinitely large, we're going to have a number that's growing out to infinity, positive infinity, divided by some constant. Well, that's still going to infinity. So as n goes to infinity, so does n go to infinity. Okay, just because of the way I created this relationship. All right, so that means that this is going to come back over here, and I'm going to replace the m, and I'm going to replace it with an n. The limit as m goes to infinity of the original one, right? The limit as m goes to infinity of this original statement over here is equivalent to the limit as n goes to infinity of this new one, once I've made this replacement. Okay, now again, the r and the t have nothing to do with n, so I can rewrite it this way. A equals to p times, parentheses, the limit as n goes to infinity of 1 plus 1 over n raised to the nth power, and then I'm going to separate this and say that this is raised to the power of RT. Okay, so remember that if we have an exponential number, like if we have 3 to the power of 2x being multiplied, that this is the same thing as 3 to the power of 2 raised to the power of x. When we have an exponential number raised to another exponent, we multiply the exponents. So for this reason, we're allowed to separate it this way. Here I had this multiplication, and then I've turned this multiplication into this number raised to another power to the power of RT. Okay, so now from our work with limits, we know that we're allowed to put this inside. This is an exponential number. This is a function. This is like a composition of functions where this is the inside function and the outside function is the variable raised to the power of RT. And because n is not in there, then we're allowed to bring it in. Okay, so let's rewrite the whole thing. Okay, so let's recap the whole thing. We started off with our formula for compound interest. We're interested in figuring out what happens to our account balance as the number of times compounded goes to infinity. So we want to find this, the limit as m goes to infinity of this formula. Good. We do a little bit of algebra magic. We just introduce a new version of 1, r over r in the exponent, rewrite it, reshuffle, and then we're going to do a substitution. Let m equal to m over r. Okay, so if we do that, then we can come back over here and replace this with an n, and replace this with a 1 over n, so 1 over n and n. Good. And now the limit as m goes to infinity, well, based on this substitution, if m is going to infinity, so is n. n is going to infinity as well. Remember, r is going to be some fixed constant. They're going to tell you what the interest rate is, and then that stays fixed as m increases. Okay, so now if the limit as m goes to infinity gets changed to the limit as n goes to infinity of this formula. Again, using a little bit of algebra magic, we know that if we have exponents being multiplied, we know we can rewrite them this way. So the difference between these two is that the exponents are being multiplied there, whereas here I have one exponential number raised to the power of another exponent. Okay, from our work with limits, we know that if we have a composition of functions, then we can bring in that limit to the inside of the function, and we're allowed to do that because this outer function doesn't have anything to do with n. This is going to be some constant chosen. And also, this is only true as long as that limit exists. So we have to make sure that limit exists. If the limit didn't exist, then we wouldn't be allowed to bring it in. Okay, so we bring it in, and so now we have the limit as n goes to infinity of just this part right here, 1 plus 1 over n to the power of n, the limit as n goes to infinity. And that gives us this, raise the power of RT, and now this looks familiar. This is exactly the definition of E. E equals to the limit as n goes to infinity of 1 plus 1 over n to the power of n. So this whole thing is just the number E, 2.718-ish, raised to the power of RT. And so there you have it. This is the formula for continuously compounded interest. So if a principal amount is invested P for a time frame T at an interest rate R, and it's compounded continuously, this formula will tell us the balance on our account. Okay, so let's look at that. Okay, so here's the formula as is presented in a more organized fashion. So continuous compound interest formula. If a principal P is invested at an annual rate R expressed as a decimal and compounded continuously, then the amount A in the account at the end of T years is given by this formula. A equals to PE to the power of RT. Okay, so that's the formula we're going to use whenever they talk about continuously compounded interest. Let's look at an example. Okay, so now let's go back to our previous example. Suppose $1,000 is deposited into a savings account that pays 5% interest per annum, so per year. Calculate the amount in the account after 20 years. And we already did it with simple interest. We did it with compound interest, compounded annually. And we did it with compounded daily. So now let's see how much would be in the account if we're compounding continuously. So remember, our formula for compounded continuously is A equals to PE to the RT. And so in this case, A equals to 1,000, that's the P, times E to the power of R, which is 0.05 times T, which is 20. Okay, so we just get our calculator and we can turn that into a nice approximation. So we want to use this button right over here that has e to the power of, let me see if I can zoom in. So this button right here has e to the power of, so we want to use that. Second, there, e to the power of, and it's 0.05 times 20 is up in the numerator. Enter. So we get that times 1,000, 2, 3. We get 27,1830. So the same amount of money invested for the same amount of time, 20 years, at an interest rate of 5%, is going to vary based on how often it is being compounded. So with simple interest at the end of 20 years, the balance in the account is 2,000. Compounded annually, the balance after 20 years will be $2,653.30. Compounded daily will be $2,718.09. And then compounded continuously gets you to $2,718.30. Notice that there is not that much of a difference. You would think that it would grow much, much faster compounded continuously, but it's actually not that big of a difference from the daily to the compounded continuously. But the formula is much easier to work with, right? Okay, so here's the results. Okay, let's take a look at this example. If $1,375 is invested at 5.25% interest compounded continuously, what is the account balance after 8 years? How much interest is earned on this investment? Okay, so going to our formula, the amount in our balance, the balance in our account will be equal to the principal invested times e to the RT. And we have everything we need. P is 1375. R is going to be here, this one, 5.25. And T is equal to 8 years. So let's just plug it in. A equals to 3175. E to the power of 0.0525 times 8 years. Okay, so now we just punch it into our calculator and get a result. So it's going to be second to the power of, so like that, and then in parentheses I'm going to put 0.0525 times 8, close parentheses, enter. And I get that decimal, and I'm going to multiply that by 1375. So I get 92.70. So at the end of 8 years, I can expect that my $1,375 has grown to $2,092.70. So what is the account balance? That's the answer to part A. This is the account balance, or the first part of the question. So this one, what is the account balance after 8 years? Here it is. The account balance is right there. Now for the other portion, how much interest is earned on this investment? For that one, all we have to do is subtract off your initial investment minus the balance your account at the end of 8 years. So for that one, it would be 2092.70 minus 1375, which will be equal to, okay, coming back to our calculator, let's subtract off 1375, and I get 717.70. So looks like this is the amount of money earned. The interest earned is $717.70. So if you wanted to get a percentage growth from the initial investment, then you could divide 770. They didn't ask for this, but it seems like a nice natural extension, right? 717.70 divided by the initial amount of 1375, and that'll get you to, so that number divided by 1375 gets you to 5220, let's say, 0.5220, which as a percentage turns into 52.20%. So looks like based on our initial investment, the initial investment has grown by 52.20% in 3 years. In 8 years. In 8 years, we have seen just a little over 50% return on our initial investment. All right, let's move on. So a bank offers a 10-year certificate of deposit, CD, that earns 2.75% compounded continuously. If 10,000 is invested in such a CD, graph the amounts of the account as a function of time for a 10-year period. So give the table values for the balances in the account for each of the years. Okay, so let's begin by writing down our formula. So A is equal to P e to the RT. And we know that this is the formula because it says compounded continuously. So when you see compounded continuously, that's how we know that this has to be the formula. The principal is given, that's 10,000. R is given, that's that rate right there. And then T is going to be the variable, right? So we want a function of T. So let's write it down as a function of T. Let's say A of T is equal to the principal, which is going to be 10,000, times e to the 0.0275 t. Right, so this is a function of t, and we can use it to graph it. Now, when we graph it on our calculator, your calculator doesn't like t's, right? They like x's. So on our calculator, we're going to come back and rewrite this as y, the output is y, equals to 1000, so 10,000, e to the power of 0.0275x. So we know that the t is being replaced by an x, and the a of t is being replaced by a y. This is what we want to put in our calculator. So let's come back to our calculator. And so what we're going to do is we're going to go over to y equals, clear anything there, and we're going to put 10,000, 10, 1, 2, 3, and then e to the power of, and then this will be 0.0275x. And so here's my function, y sub 1. I can go to my tables. Remember to go to table set, second table set. Make sure this is under ask, this is under auto. If it's not like that, use your arrows to change it. Okay, we want to go over to table, second table. Let's delete anything that's there. And now let's put in, it says give a table balance for each of the years. Okay, so after 1 year, this is my balance on my account after 1 year, $10,279. After 2 years, after 3 years, after 4 years, after 5, 6, 7, 8, 9, and 10. Okay, so here's my account balances. If I want to get a more specific one, I can use my arrows and go up like this and find it. So after 1 year, this is the account balance, $10,278.82. After 2 years, this is the account balance, $10,565.41, and so on and so forth. So we can see the account balance is growing. Okay, so it says, let's see, did we answer everything? Graph the amounts of the function of 10-year period. Okay, so now let's write down the graph of this. So we're going to go over to y equals, make sure that that's the only equation on there. Also, make sure that these things up here, plot 1, plot 2, and plot 3, that they are not active. See how this equal sign is dark? That means it's active. These equal signs are not dark. That means that they are inactive. These are inactive as of now, and this is what they would look like if they were active. They would have like a dark box. Now plot 1 is active. We want to deactivate it. Okay, so I want all of them to look like these, not like that one. So if you use your arrows and highlight it and hit enter, you can move away, and that's how you activate, turn it on, turn it off, right? So make sure that they're all off. Okay, so now that they're all deactivated like this, we're going to go over where it says window, and we're going to type in the window that we're interested in. So the input values are going to range from 0 through 10. So let's just go a little bit farther to the left. So let's go from -1 through 11. That should capture what I'm interested in, between 0 and 10. And the output values, well, I can already tell that they're going to be dancing around the neighborhood of 10,000. So I can see that I want this to go from, say, $0 all the way up to, say, about 15,000. Let's see if that's enough. We can always come back and change this if it's not enough. So that's 15,000. And let's see what that looks like. When you're done, you can just hit graph and see what you got. Okay, so this is the line we got from our graph. Okay, so we could see that it's slowly growing. If I want to see what values are on there, I can hit this button that says trace. And then I could see the equation up here. That's the green one. And I can see that this is the ordered pair 5, $11,474. So at exactly, when x equals to exactly 5, at the end of 5 years, this would be the balance on the account, $11,474 and about 2 pennies. Okay. However, we know that time is continuous. It's not just 1 year, 2 year, 3 year. This is being compounded continuously every second of every minute of every day. So we can just kind of slide back and forth here and find the balance on our account on any specific interval of time. So this is after 1.2727273 years. This would be the balance on our account. So we can figure out exactly how many days into the after the first year is this. Right? We can turn we can turn a number of days, for instance, into a percentage of a year, and then we can figure out exactly how many years this represents. So time is continuous, and this is being compounded continuously, so we can slide back and forth and find different values. So, for example, this one is approximately 3.5454 years, a little bit more than 3.5 years, 3 years, 6 months, for example. And we could see that the balance on my account at that point would be $11,024.11. Okay, so we can see how it grows this way. Okay, so that's how you can do it on your calculator. You can create a graph this way. We can also create our table to give us the results. So I think that answers this. But let's do it on Desmos. It does such a nice job of graphing things. So if we go to Desmos, okay, so if I just put our graph, our equation right on here onto Desmos, f of x equals to 10,000 e to the power of 0.0275x. I can see that this is the result here. So this is going to represent the balance of our account. If we start off with 10,000, you can see that it grows as time goes by. And then it probably doesn't make any sense in terms of this real world situation for us to go negative in this direction. But there might be a context in which it might make sense. It might be that this account has already been growing under these conditions up to a certain point, right? We just catch it at a particular point, and we want to know what was the balance before that, right? So zero is not necessarily that's when time begins, or even that's when the account begins. Zero could just mean the point when I started checking in on the balance of the account. Maybe, for example, I worked for the FBI and I found this account that's kind of suspicious, and I start paying attention to it. So zero could mean January 2020 because that's when I started paying attention to it. But maybe -1 means 1 year before I started paying attention, or 2 years, or 3 years, or 4 years, and perhaps it's been growing all along. So there could be a situation in which maybe negatives might make sense, but for the most part, most word problems, zero is the beginning of when you start paying attention, perhaps when the account is first open or the investment is initially made. That could be considered zero. But keep in mind, we can always change that. It's an arbitrary location to start. At any rate, so this is how it grows. And so I could also identify a point on my grid. And so you can see that this means after 55 years, this will be the balance in my account, right? So as I go out this way, we see that the balance on your account just grows. Okay, but they were really just interested in this tiny little segment between 0 and 10. So let's just zoom into here. So between an investment of 0, that's where you started with 10,000, and then you grow as time goes by, and as you grow from 0 to 10 years. So we get to this point over here at 10. At 10, this is our final balance on our account after 10 years, $13,165 and about 31 cents. Also notice that it almost looks like a straight line, right? It isn't though, but we've zoomed in so much that it almost looks like a straight line. Don't let that fool you. Graphs can easily trick us sometimes. Okay, if we zoom out, we get a better sense of how it's growing exponentially. Good. As long as we're looking at things, solutions with graphs, one great way to solve a very popular kind of question is to ask, when will the account reach a certain level? Like you might be asked, when will this $10,000 investment reach $1 million? Okay, this is the $1 million markup here. Let me count the number of zeros here. 1, 2, 3, 4. Okay, it's kind of hard to tell the zero. So let's do this. Let's put a horizontal line, y equals to 1 with 1, 2, 3, 4, 5, 6 zeros. There it is. Okay, so that one wasn't it. That one was 100,000. Here is 6 zeros. That's 1 million. This blue line across is 1 million. And so I can see that this investment will grow, but it's not going to quite get there. According to this, after 55 years, the balance in my account will only be $45,380. So it still has quite a bit to go. So let's change this guy. Okay, so if we allow ourselves to grow past that after 70 years, after 81 years, after 100 years, now we start to really see those that investment payoff. Grows a lot more, right? Notice that 1 year here going from 136 to 137 makes a really big difference. You grow a lot there. And that's because you have such a large balance in your account and it's earning interest, that the amount of interest you earn makes more money, right? So this is how rich people stay rich. They already have a lot of money and it's growing. They're in the amount of interest that they're earning on it is just excessive. right? Someone that's a billionaire can just sit around and watch TV all day, and their $1 billion makes them tens of millions of dollars in a single day, just just by sitting there, just by earning interest. Okay, so moving on, we can see where they cross. So we can kind of go up there. We can kind of guess it a little bit, right, based on this. Okay, but if we wanted an even better way of finding it, what we could do is find where they cross, right? So find that intersect point right there. Now Desmos will do a nice job of just finding it for us. It's at 167.46. So at 167.46, it's going to get really close. So there's some rounding issues, but it's going to be really close to 167.46. So it's really close to 167 and a half. So 167 and a half years after investing $10,000 at 2.75% will you reach $1 million. Right? That's what this says. Also, if you wanted to find it by hand, right? So if you don't have, if this isn't allowed, if you're not allowed to use a graphing device to find this, then we could do the following work, right? So the question is, when will this investment reach $1 million? So what we could do is set it equal to $1 million. We're going to take our equation and set it up over here and say, when will this balance equal to $1 million? Let's divide both sides. So we get 1 million. Like that. So really it's only going to be 100. So we get whenever 100 equals to e to the 0.0275 t. And from our work with logs, we know that we take the log of both sides. So ln of 100 equals to ln of e to the 0.0275t. And so we know that this is going to be ln of 100 equals to, now these two are inverse operations, so we just end up getting 0.0275t. Divide both sides by this decimal. I'm going to flip it around as well and say that t is equal to ln of 100 divided by 0.0275. Okay, so now we can just get our calculator, quit out of here, clear, and say ln, so this is this button right here, ln of 100, close, divided by 0.0275. There you go, 167.46 years. Okay, so I can rephrase the question and say, if I invested $10,000 today at an interest rate of 2.75% compounded continuously, how long will it take for my $10,000 investment to grow into $1 million, right? And so the answer would be, it's going to take 167 and a half years. So we add today's date plus 167. And we'll be able to reach our approximation. Now remember the 0.46, what we could do is multiply, this is in years, so we can multiply the 0.46 times 12 to figure out what month it is, and it's going to be approximately the 6th month. So 0.46 times 12 gets you to 0.46 times 12 equals to 5.52. So 5 months and then 0.52 of the following month. So we can do 0.52 times approximately 30 days. So that'd be 15 days. Okay, so let me write down. This is 5.52, so this would be 5 months. And this is going to be 0.52 of a month. So we can come back over here and multiply 0.52 times approximately 30, and that gets us to approximately 15, and I'll just round it off there. 15.6. 15.6. Okay, so this 167.46 years, so 167.46 years is the same thing as 167 years, 5 months, and 15 days. Okay, so today is March 7th, 2021. Okay, so today is March 7th, year is 2021. So if I invest today, the 10,000, in what calendar year, what calendar date will I be a millionaire? All right, well, I got to add, I got to add 167 years to this one. That'll get me to the year 2188. And then March is the third month, March, and I got to add 5 to that. That'll get me to the 8th month. And day 7, I got to add 15 days to that. That'll get me to day 22. So that's my answer. If I invest $10,000 today on March 7th, 2021, by the 8th month, which is August, by August 22nd, the year 2188, I will be a millionaire. Okay, good. Okay, let's do another example. Okay, how long will it take an investment of $8,200 to grow to $14,500 if it is invested at 9.35% compounded continuously? Okay, well, this is a very similar example to the one we've just done. So again, let's go back to writing down, or let's start off by writing down our formula for continuously compounded interest. So that would be A equals to P e to the RT. And we know the initial investment is $8,200. We know the final result would be $14,500. And we know that the interest rate is 9.35. The only thing we don't know is how long, right? So the T is the unknown. Okay, so let's write down all the ones we do know. So we know 14,500 is the final balance of my account when an initial investment of $8,200 is made, and it's compounded continuously with an interest rate of 0.0935 T. Okay, so we just have to solve for T. That means that this would be 14,500 divided by 8,200 would be equal to e to the 0.0935 T. Okay, a couple zeros there cancel. 0, 0, 0, 0. I wouldn't convert it into a decimal, then we already have a problem with rounding, so let's just leave it alone. So this equals to e to the 0.0935 T. We're going to take the ln of both sides, so ln of this side, 145 over 82, equals ln of the other side, e to the 0.0935 T. Okay, these are inverse operations. They undo each other. So that means that this is going to be equal to ln of 145 divided by 82. And that's going to be equal to 0.0935 T. Good. So now just divide both sides by that decimal. That'll solve for T. So I'll just flip it around and say that T is equal to ln of 145 divided by 82. and the whole thing divided by 0.0935. Okay, so now we just take our calculator and find an approximate answer here. So this would be 145 divided by 82 gets you to that decimal. And so now ln of that decimal, I hit second ants to give me the previous answer. Right? Otherwise, you could just type in the whole thing inside the ln function. So that, or you could also just type in ln of and then type in the 145 divided by 82. Same thing. Get the same decimal. And now that decimal gets divided by this decimal. So that one is going to be divided by 0.0935. Enter, and that's what we get. 6.00964. .0964, rounding to 4 decimal places. So that's how long it's going to take, and this is in years. Years, right? 6.0964 years, and again, we can convert it into months and days. So if we multiply 0.0964 times 12 months, what are we going to get? Let's go back to our calculator. So 0.0964 times 12 means that it's 1, so it's 1 month, and then there's 0.1568 months beyond the first month, right? So it's really 15% of the next month. So that'll be 1.1568, 1.1568 months. So 0.0964 years is really 1.1568 months. So now if we multiply the 0.1568 times approximately 30 days in 1 month, we get 0.1568 times 30 gets us to about 4.704. 4.704 days. Okay, so we can say that it's going to take 6 years, 1 month, 4 days for us to reach, for our investment to grow from $8,200 to $14,500. Okay. It will take 6 years, 1 month, and 4 days for an investment of $8,200 to grow to $14,500 at a rate of 9.35% compounded continuously. Okay, how long will it take for an investment to double if it is invested at a rate of 3.25% compounded continuously? Okay, note that the actual amount invested is not given here, right? So that's okay. We go back to our formula. This is equal to A equals to P e to the R T. R is given. T is what we want to find out. How long will it take? But P is not given. They don't tell us how much we're going to invest. All we know is that we're going to double our investment. So if we're going to double our investment, that means that at the end of the time period, whatever it is, our account balance would be twice as big as P. Okay, so to double our initial investment of capital P, then A should be equal to twice P, right? We've doubled it. Note that this is not this. That's a very common mistake. P to the power of 2 is very different than twice P. Doubling is twice P, not P squared. Okay, so armed with that knowledge, we're just going to replace the a with a 2p. Right? At the end of t time, find t such that this is true. E to the r t. And so now we know r is 0.0325, and t is what we're looking for. And notice what happens to p. When we want to double it, this is going to work out really nicely because, let's just put it over here. This is going to be 2p equals to p e to the rt, and if we divide both sides by p, divide by p, these p's cancel, these p's cancel. So then p is no longer relative. Right? You can just kind of ignore it and say that the formula then becomes 2 equals to e to the rt. Good. Okay, so r is given, but let's practice not plugging it in yet. It is some constant. We know we have it. It's this one. Imagine that I gave you a bunch of questions like this for homework, and one of them has 3.25, and another question has 5.72, and another question has 9.08, and just a bunch of them. You don't want to redo all of this work for every single one of them. Why don't we leave it alone? Solve it, knowing that r is a constant that we have a value for, that we will have a value for, and solve for t. Okay, so now we take the ln of both sides. So this would be ln of 2 equals to ln of e to the rt. Good. These two operations cancel each other out. This is just some constant, just some decimal number. We can use our calculator to find it. And so we end up with ln of 2 equals to rt. And so now if we divide by r, we get that t equals to ln of 2 divided by r. Okay, so armed with that, now we can find the answer. T equals to ln of 2 divided by r, which is 0.0325. Okay, so now we can get our calculator. Clear? Clear. So this would be ln of 2 close divided by 0.0325. So it looks like 2132.76. 31 years. Okay, so let's play again with the same transformation. Telling someone 31.3276 years doesn't really mean much. Most people would prefer to have it in years, months, and days, right? So let's convert this. So this is years, 0.3276 times 12 months. What is that going to be? 0.3276 times 12. 393.12. 3.9312. And this is months. Okay, so now what is this in terms of months? So let's change that to days. 0.9312 times approximately 30 days in 1 month. Let's come back over here. That's going to be 0.9312 times 30. Gets us to 27.936. And that's as far as we want to go. So this 21.3276 years is equivalent to 21 years, 3 months, and 27 days. Okay, so it takes 21.3276 years, or 21 years, 3 months, and 27 days to double your investment, right? And again, notice that this was independent of the actual amount invested. So this exact same time frame stays the same whether you invest $1,000 and you want to know when it turns into $2,000, or if you invest $30 million into something and you want to know when it goes into $60 million, right? Just doubling your investment, whatever that is. Okay, so now notice that in the middle of solving this problem, we solved for T in general, right? So whenever you want to double an investment and you are given the interest rate and you just want to know how long it takes to double your investment, here's your formula. So this is one of those boxed up formulas people have, just how long does it take to double your investment? Here it is, ln of 2 divided by r, where r is the annual interest rate, and this will give you t, the length of time it takes to double your investment. It doesn't matter what the investment is, could be $100, could be $1 million, could be $2 billion, it doesn't matter. How long does it take to double it? Okay, and then further, notice that the way we got it was to replace A with twice P. But what if we wanted to triple our investment, right? We're not satisfied with doubling it. We want to triple our investment. So how would that change in this formula? Instead of 2P, we go, okay, we want to triple it. We want to 3P it. Triple. We want to triple our money. How long does it take to triple our money? Doubling is not good enough. Okay, so all we do is change this from a 2P to a 3P, which means that this changes to a 3P. P still cancel, P still cancel. We have a 3 there. We'll end up with a 3 over here. And so we'll end up with a 3 over there and a 3 over there and there. We'll get a 3 over there. It's a very simple pattern. If there's a 2 in there, that means we're doubling it. If there's a 3 in there, that means we're tripling it. Okay? And that's a nice pattern that we can establish. So here it is. So the doubling time for continuous compounded growth at R interest rate expressed as a decimal can be found using this formula R. And then tripling it would be T equals to ln of 3 over R. And quadrupling your investment would be T equals to ln of 4 over R. Right? So pretty straightforward formulas. Okay, so I think this should be enough to get you started on your homework. Please let me know if you have any problems, questions, or issues.
Do your homework.